What we're doing is we're going to look at the modern view of the atom. Let's start there. So to start understanding chemistry, we got to start on the small scale first. All right, so atoms consist of three parts. Protons and neutrons are in the nucleus, and electrons are found outside the nucleus. The protons are positively charged, the neutrons are neutral, as the name suggests. They have no charge. Electrons are found outside the nucleus and negatively charged. The proton's positive charge is equal in magnitude to the electron's negative charge, but they're opposite in signs. In other words, for every one proton, that one positive one will balance out with the negative one from the electron. Protons and electrons just have the opposite charge. They balance each other out. But there's another big difference, or there's another note here. There's a big difference. Look at the mass. The mass of a proton is somewhere around 10 to the minus 27 kilograms, whereas the mass of the electron is somewhere around 10 to the minus 31 kilograms. And so what that means is that the electrons are far, far, far lighter than the protons. They're so much smaller than the protons. When the protons and the electrons match up, that's neutral. When the electrons are gained and lost, those are called ions. Ions are formed when an atom or a group of atoms gain or lose electrons. It's not shown here, but it's a good idea to draw this in. If I were you, what I would do is just draw your staircase right in here. So starting with boron and dividing up with boron and aluminum, just do this diagonal staircase. And that's really important. That's where we're going to start the lesson. That is the separation between the metals and the non-metals. And that's one of the first things you need to recognize when we start naming some compounds. The metals on the left, the non-metals are on the right of that staircase. Isotopes are atoms of the same element, but they're different. And how are they different? Because they can have different numbers of neutrons. And so that's one of the first things, even in a general chemistry course that we teach. The first things we learn are that we have elements that are made up of atoms. So you have carbon is made up of carbon atoms, but carbon atoms in the universe can be different. Not every carbon atom is going to be the same. They can be different because they can have different numbers of neutrons. And those are what are called isotopes. Okay, so the way we're going to represent isotopes is by writing the elemental symbol. And in the subscript, this is going to be the atomic number, protons in the nucleus. And then this number is called the mass number. So the mass number is going to be the protons plus the neutrons. Very simple calculation. That's all it is. Protons plus neutrons. If there is a charge, if ion, right? If there is a charge, then you have to put the charge in the top right-hand superscript. So right up here, if there is a charge. Now, the way there's going to be a charge is if protons and electrons are different. If protons and electrons are different, then you'll have a net charge. So this is what we're given. So what they want us to do is to select the symbol and what is the charge. The first thing we should recognize right here, the protons and the electrons are off. They're different. What is the net charge? Simple formula, protons minus electrons. 37 positives, we subtract 36 negatives, and so the net is -1. You don't have to write the number 1, we can just say negative sign and that's fine. 37 protons, so protons is the atomic number. So we go to the table, look for 37, there you go, Rb, rubidium, and then on top of rubidium, we'll put the positive charge, like that. Now, they're not asking about isotopes, so we won't worry about that. And so let's start with the alkali metals. So over here on the alkali metal side, we already saw one example here. On this first family right here, the alkali metal family, these elements, when they do exist as ions, will typically form a +1 ion. So they typically lose 1 electron and become +1. The earth alkali metals, that second family, they typically lose 2 electrons and they become a +2 charge. Now, let me pause there because that's important. That's important because when we're going to do names here in just a second, when I ask you about ions, I'm going to ask you about the sodium ion. And so what's the charge in it? You're automatically going to say alkali metal ion. These are all +1. Sodium's a +1. What's the charge in a potassium ion? +1. That's it. Calcium, strontium, +2. That's it. Magnesium, +2. Over on the right-hand side, you'll notice the noble gases. The noble gases, we're going to learn later, these are pretty stable. They rarely react. They don't want to gain or lose electrons. You'll see why in the next chapter in another week. So these atoms typically exist as just neutral atoms, so you can put a 0 up there. The next family has a special name. These are called halogens. And the halogens, fluorine, chlorine, bromine, iodine, these all are -1. When I ask you about bromine, iodine, what's the common charge? You're going to automatically say -1, and that's it. There's just two more. There's not a specific name here. I just refer to them. I'll just say the oxygen family or the family with oxygen and sulfur. These are all -2. Nitrogen, phosphorus are -3, and then we'll stop there. The transition metals, okay, all of these elements here, these are metals. The metals will typically lose electrons to become positives, but the transition metals can have different charges. In other words, take a look at iron, for example. Iron, Fe, can exist as a +2. It can also exist as a +3. Copper, for example, can exist as a +1, but it can also exist as a +2. And so when we name our compounds, we're going to have special rules. So let's start with covalent because those tend to be the easiest. The rules are pretty simple. When you see a nonmetal and a nonmetal in a compound, you use these rules. There's no ions present, so there's no need to balance any charges. Name the first element using the full element name, and name the second element as if though it were an anion. And so what's going to happen there is you're going to have a suffix change. So all of these second elements, you're going to have the suffix "ide." So you're going to change the suffix there. So these are for covalent or non-metal, non-metal. And they're pretty easy. Most students like naming non-metal, non-metal. We tell the reader how many atoms there are by using prefixes. Everybody should know the first 10, and I think most people remember the first 10. And so you always use prefixes. And rule number 5, just a caveat here, you never use the prefix mono at the beginning. Otherwise, you use prefixes for everything. To write a chemical formula, you're going to write the elemental symbol. So you see N represents the element nitrogen. O represents the element oxygen. Both of these elements are nonmetals, and so we're going to use the nonmetal rules. So when you identify that, you don't sit, you, there's no charges. Don't worry about charges. When it's nonmetal, nonmetal, you just use prefixes. So for nonmetal, nonmetal, there's 2 nitrogens, dinitrogen. There's 5 oxygens. The prefix for 5 is penta. But because this is an oxygen, now remember for oxygen, we're going to change that second element name, change it to oxide. And whenever you see this, this double vowel, when you see an A before an O, just drop that first vowel. This is going to be pentoxide. Dinitrogen, pentoxide. So you do this for double vowels except for I. So whenever you have a double vowel, drop the first one except for I. And I'll show you an example here in a minute. S is the symbol for sulfur. Cl is a symbol for chlorine. These two are nonmetals, so we don't worry about any charges. We're going to name this by just using prefixes. Disulfur, dichloride, and that's it. Okay, you know what? I told you I was going to show you an example. Let me show you. Here's an excellent example. This is one that everybody knows. CO2. Everybody has said this name, but now you know the rules. So this is called carbon dioxide. This is one of those examples I showed you. It's a double vowel. It's an IO, but you go ahead and keep the I's, right? So whenever you have double vowels like pentoxide, you drop that first vowel, but if you have an I, you keep it. So like dioxide, so you keep it like that. Diboron trioxide. Pretty simple, right? Just give the symbol B subscript 2 and then O3 trioxide, and that's it. All right, here we go. This is fun. We actually get to do some work now. All right, so the important thing to remember here that these are all non-metal bonding with non-metal. So let's write the names. The formula is given to us. Let's write the names. Okay, so we have to use prefixes. So here you see there's 3 carbons, and the prefix for 3 is tri. We name the first element with its elemental name. The second element, we name it, we have to use the prefix mono for the second element to say that there's one. This is a sulfur. Whoops, misspelled it. But we need to change the suffix. So that's an important detail here. We need to change the suffix to sulfide. S2F10. So this is a sulfur, and there's 2 of them. So we'll write disulfur. So we use the elemental name. The second element is where we change that suffix, and that's just a rule of these nonmetals. So this will be a 10, this will be a decafluoride. Disulfur decafluoride. A Br, the symbol for Br is bromine. And there's only one bromine. Okay, so this is a good example. There's only one bromine. We use prefixes for everything except when there's one at the beginning, you never use mono at the beginning. Never use mono for the first element. That's it right there. Just say bromine. Now this is F3, so F is fluorine. So we'll say tri, and we'll change fluorine to fluoride. Tetraphosphorus, yeah, tetraphosphorus. 7 is hept. Hepta is the prefix for 7. Now, there's a rule here. When you see this double vowel, then you'll drop one of them. There's 2 exceptions, but yeah, when you see a double vowel like this, you'll drop the first one and just say heptoxide. Now, the exceptions, keep di and tri. So for example, dioxide. So you wouldn't drop that I. Triiodide, triiodide. You wouldn't drop the I. So for the formula, this is something that everybody has seen. Most people know what this is. The name for the ionic compound is we take the parent name, so the first element is named first. So Na is the name for sodium, and Cl is the name for chlorine. However, this is not a chlorine. This is an ionic compound. And so that means there are ions present. Okay, so let me go to Christian. Are you there, Christian? Do you remember the charge? What's the charge on a sodium?
It's 1.
That's right. So right on the table, just look up at the top, +1. And we'll go to Javier next. Javier, what's the charge on the chlorine when it becomes an ion?
-1.
That's right. So this is a really important take-home message. On your charts, so I'm looking at my references right here. I'm looking at the references. So everyone's going to have this. Make sure you print this out for your quiz and exam. There's Cl minus. Notice the suffix change. So for anions, this is not a chlorine anymore. When chlorine accepts an electron to become -1, the name changes to chloride. So notice that suffix change. So Cl is called, or Cl minus, I'm sorry, chloride. Okay. Now, there was one important thing here. There's one important thing. Ionic compounds are typically metal with non-metal, typically. Now, I say typically because, whenever you see metals and non-metals, so sodium's a metal, chlorine is on the non-metal side. So right there is your, marker to say this is an ionic compound. But also just be aware that there are polyatomic ions that exist. Let me show you just a few of those, just so you're familiar. So just be aware. So this is on the second page of your references. This is the one that's on Blackboard. This page shows common cations, and so cations means positive. And so I just want to point this out because you'll see some polyatomics. These are just a few. I mean, there could be others that you might come across. Look at this one. This one says NH4. This is nitrogen and 4 hydrogen atoms. But this forms a molecule. The nitrogen and the hydrogen atoms are forming bonds. So it's a group of atoms, but the group of atoms has a net charge of +1. And so this would be considered a cation. So that has a name. It's called ammonium. So whenever you see NH4s with a positive charge, that's when you're going to use this name, ammonium. And I'll show you the second page. Some of you may have noticed already. We have several anions. Anions are negatively charged. Okay. Um, there's several anions. There's several polyatomics. So you'll notice a lot of these have more than one atom, right? And so here's some common ones: bicarbonate, right? This is the baking soda. Sodium bicarbonate is baking soda. Right here, bicarbonate has a hydrogen atom, a carbon atom, three oxygen atoms, and notice there's a net charge of -1. Okay, right above there, you see acetate. Now, you see it written two ways. You'll usually see it written the second way here in our class. This first way, you'll usually see it an organic chemistry class. But acetate has two carbon atoms, three hydrogen atoms, and two oxygen atoms, and it has a net charge of -1. Okay, so these are all anions. And so look at the monatomic. Monatomic means single atom. So chloride, fluoride, there's a couple more here, iodide, nitride. So we saw some of those, oxide, right? O -2. And then you have the polyatomics. Okay. All right. So in the book, we had another, oh, I'm sorry, and the charges have to balance. That's why there's one sodium and one chloride. Okay, you don't write the number one, but when you see the symbol once, that's what that means. There's one sodium plus one, there's one chloride minus one. When I ask you the charge on a chlorine or chloride for anything, you're going to say -1. So Joanna's asking about these charges right here. And let me say it slow, and everybody listen here, and then you can go back and watch it on the video. These are not charges. -1 plus 1 plus 3 plus 5 plus 7. These are not charges. If we go over here, thank you for bringing this up. That way nobody's confused. These are called oxidation states. And we're going to talk about that in chapter, ooh, I forgot the chapter. It's the electrochemistry. It's the electrochemistry. So these are called oxidation states. You don't know the definition now, but we'll get to it in a few weeks. So let me be clear for everybody here and watching on the video. You look on the periodic table, you're going to see some positive and negative charges here. These are not charges, these are oxidation states. So you're right, for chlorine, chlorine's a monster. It's got several oxidation states. Look at nitrogen. Nitrogen's a monster too. It's got a ton of oxidation states. And I'll explain those when we actually get to redox reactions
Thank
later this
you.
semester. No, well, thank you for bringing that up. I forgot about that. That's another mistake, some students ask, what's the charge? But these are oxidation states, not charges. Um, okay, K2O. All right, right here, you notice that K is an alkali metal. O, of course, we saw that, is oxygen, a nonmetal. So again, when you see metal with nonmetal, this is an ionic compound, so we have ions. All right. The charge on a potassium is a +1 always. You see that there's two of them. So you have to write the subscript 2 because oxygen is a 2 negative. The ratio here is 2 to 1. There's two potassiums for every one oxygen. So that's an empirical formula too. The empirical formula tells you the ratio, 2 to 1, right? For sodium chloride, the ratio is 1 to 1. So the ratio is the simplest whole number ratio. That's the empirical formula, simplest whole number ratio. And before we leave, I'll go back and work on that problem so you can see it. It's pretty easy to understand. Okay, what's the name here? Straightforward, potassium. O2 negative. Now be careful there. We got to name it with the anion name. So O2 negative is oxide. So you change the suffix. Potassium oxide. By the way, everybody, for ionic compounds, you do not use prefixes. You don't say dipotassium. You don't have to do that because when you see potassium oxide, oxide's a 2 negative, you need to balance the 2 negative with 2 positive charges. And so you don't need to say dipotassium. When you write the formula, you know that there has to be 2 potassiums. All right, so let's not freak out here. It looks very busy. It is very busy. There's a lot going on there, but we've learned a couple things so far. So, number one, these are all binary compounds. So, binary means 2 parts. If you look at the first part, what you recognize is this combination of NH4. And I just showed you a second ago, when you see NH4 grouped together, that's always going to carry a positive sign because that, of course, is ammonia. And I showed you that right here, ammonia, NH4 plus. Now, you see that ammonia is present 3 times. Okay, so I'm just going to show this so everybody can see it. Outside of the parentheses, you see 3. Now, the parentheses is important. And the rule here is when you have more than one polyatomic, you have to write the parentheses. That makes sense because if you don't have the parentheses, what does it look like? It's going to look like NH43, right? If you're missing the parentheses. So of course that's wrong. So notice I didn't need parentheses around potassium. Potassium is just 1, right? It's just 1 element or 1 ion. And so K2 just means 2 positives, 2K plus. But when you have a polyatomic, more than one time, you have to write the parentheses. Now, look at the second part, PO4. So when you see PO4 as part of this, this is ionic, of course. These are ions. So when you see PO4, let's go to our anion chart, and you see PO4 is called phosphate right here. And the whole polyatomic has a net charge of -3. So PO4 -3. So the name for this, ammonium phosphate. And that's it. COSO4. Okay. Now, this is special because we see the element CO. Now, where's my table? Now, that's special because CO is cobalt, and cobalt is a metal, but it's a transition metal. Now, what was special about transition metals? They can have different ionic states. Cobalt can be usually a +2, +3. By the way, I know it says +2, +3 here, and that's because for these metals, a lot of times the oxidation state is the same as the charge. So that can happen, but try to ignore that. Yeah, cobalt can have different charges. So with transition metals, we have to tell the reader what the charge is. Is that a cobalt 2? Is it a cobalt 3? Okay, we don't know, but what we do know, we know SO4. So if you go to your tables, let's go to SO4. SO4 is called sulfate. and SO4 has a net charge of -2. So watch what we're going to do here. There's one SO4 with a -2 charge. And so therefore, for ionic compounds, we want to take this one cobalt and give it a charge so that these balance. So what's the charge on a cobalt? +2. All right, now let's name it. And if you have your notes, you can follow along, but I'll show you here. With transition metals, you have to tell the reader what the charge is. So you can't just say cobalt sulfate. You can't do that. So what we're going to do is we're going to put Roman numerals in here, and the Roman numeral is going to tell us what the charge is. This is a metal, copper is a metal, bromide is the nonmetal. So again, identify that this is ionic. Now there's a Roman numeral here, and the reason for the Roman numeral, like I said, for transition metals, you have to tell the reader what the charge is. The elemental symbol is Cu, Cu, and the charge is 2, so the Roman numeral is 2, so the charge is +2 on this ion. Now bromide, that's a nonmetal. Bromine is the parent name, but of course it's called bromide because it's an anion. And for monatomic ions, right, it's just a bromine by itself, bromide. What's the common charge? -1. Let's write the formula for ionic compounds. Just make sure that the charges balance. The simplest thing to do here is to use this crisscross method. Bring the 2 down here, bring the 1 over here. Not the charges, don't write plus or negative, just write Cu1 Br subscript 2. Okay, that's the easiest thing to do. Copper 2 bromide.